In this video, we are going to learn how to perform real-time single and multiple object detections under the environment of Colab. And to be specific, we are going to train YOLO with custom objects in Colab and apply the trained network to perform custom object detections with the use of OpenCV. You only look once YOLO is a state-of-the-art real-time object detection system. YOLO is a deep learning algorithm which came out in May 2016, and it quickly became so popular because it is so fast compared with the other deep learning object detections models. Traditionally, recurrent convolution neural network applies regions to localize the object to perform object detections, which means that the model is applied to multiple regions within an image. And then the model computes scores to an image at multiple locations and scales. High scores regions of an image are considered as an object is detected. On the other hand, YOLO used a totally different approach. Instead of selecting some regions, they apply a single neural network to the full image and predicts bouncing boxes and probability for each region. These bouncing boxes are weighted by the predicted probabilities. And if the probabilities are higher than the threshold that can be set by the users, the object is considered as detected. Since it only scans the image once to make the predictions as compared to other algorithms which requires multiple scans, it is faster in practice. And that's why this is called you only look once YOLO. The latest versions of YOLO is YOLO version 3. YOLO version 3 uses a few tricks to improve the training and increase the performance, including multi-scale predictions, a better backbone classifiers, and few more minor techniques. This recent version is more powerful than the basics YOLO and also the YOLO version 2. And in this video, we are going to apply the YOLO version 3. YOLO version 3 is extremely fast and accurate. As shown in the picture, in mean average precisions measured at 0.5, YOLO version 3 is about 4 times faster than the other algorithms. Also, you can easily trade off between speed and accuracy, simply by changing or selecting the size of the models without retraining the models again. Our inputs can be in 3 forms: image file, webcam feed, video files. And with the use of the pre-trained YOLO models, it can detect up to 80 objects, such as person, bicycle, car, motorbike, aeroplane, bus, and etc. If you want to know more about that, you can refer to the COCO files for details. Before we move on, I want to introduce a transfer learning concept, which is a very important and interesting benefit of applying deep learning neural network. Because very often we are solving a different but yet somehow similar problems. To take advantage from others' work and to speed up our training process, we usually can reuse partly or wholly from others' pre-trained network to accelerate our own training and solve our own problems. In deep learning, this concept is called transfer learning. This means that we're using the weights in one or more layers from a pre-trained neural network model in a new model. By keeping the weight and fine-tuning the weight or adapting the weight entirely when training a new model. So to customize our own object detections, we will apply the transfer learning concept. We will download the pre-trained convolution nodes weight from Alice's AB, and then we can play with different hyperparameters, and most importantly, our own dataset. In other words, for training our own custom object, we will use the convolution nodes weights that are pre-trained, and then we will start our own training from that particular trained weight in such a way that we don't have to retrain everything from scratch again. However, to retrain the YOLO, we need a decent GPU in order for us to speed up our own training. And it comes with the help of Colab. Google Colab is a free cloud service based on Jupyter notebooks for machine learning education and research. It provides a runtime fully configured for deep learning and free of charge access to a robust GPU. Colab is the perfect space to do your research, tutorials, or projects. However, not everything can be wonderful. Colab has some limitations that can make some steps a little bit hard or tedious, and we will discuss how we tackle some of the limitations. Before we talk about the limitations, let's learn a bit of the Colab environment. Colab supports Jupyter notebooks, also known as IPython. Traditionally, when working interactively with the standard Python interpreter, one of the frustrations is the need to switch between multiple windows to access Python tools and system command tools. IPython bridges this gap and gives you a syntax for executing shell commands directly from within the IPython terminal. The magic happens with the exclamation point. Anything that appears after that on a line will be executed not by the Python kernel, but by the system command line, and that is a Unix-like system. This is a very important concept when you're working in Colab, because there's no command windows over there. You need to use the exclamation point to perform system commands, such as creating files, creating folders, saving files, amending folders, and etc. In this way, you can work with Colab's environments to perform both Python functions and system command. Although Colabs provide you a decent GPU and a seamlessly IPython environment, there are two main problems. The first and main problem is that Colab's runtime is volatile. Your virtual machine will blow up after 12 hours, and everything will disappear after that. This means that your virtual machine and all files are lost after 12 hours, and you will have to reconfigure your runtime in order for you to restart your training again. And this can take some time each time we need to restart the virtual machine again and again. The second problem is that under the collapsed environment, you're working with a remote virtual machine. That means you don't have the direct access to the virtual machine file system, so that you have to upload your files every time, and also you have to download the files created during the training. Lucky that Google provides us a Google Drive to solve the problems of volatile virtual machine and remote file systems. Google has included the Drive API on the notebook, making us very easily to map to our Google Drive as a virtual machine drive, so that we can save our files directly to the mapped drive and rescue our files before the 12 hours terminations. And besides, we can also synchronize one folders in our computers to Google Drive, so that we can have direct access to the Colab file system, and we will be able to work with YOLO configuration files locally and test on the notebook instantly. In short, with the use of Colab and Google Drive, we can now train our custom objects with GPU in the cloud environment, and we will then download the final convolutional weights into our local computers for custom object detection. To start custom object detections, we need to prepare our image dataset in our local computer. If you search image in the internet with the use of Chrome, you can download all image once with the link shown in the step 1. And of course, you can prepare your own image from different sources, or even you can take photos by yourself. As a rule of thumb, it would be better if you could have at least 100 different images for every individual object detections. And of course, the more the better, especially when you're working with multiple object detections. Once you have your own custom objects image, you can then download label image, which is a which is a graphical image annotations tools for use to annotate your image and prepare a recognized text format for YOLO training. And after we label all images, we can then store all images and then their corresponding text files in a folder. And then we zip it and for uploading. And in step 2, we need to set up a Google Drive account for uploading and downloading the files between Colab and our local drive. In our example, we will create a folder called Yolov3 in Google Drive and upload our zipped image datasets into it. Just in case if you wanted to rename them, please make sure you also revise the codes in the Jupyter notebook. But that should be not too hard to make everything aligned. Apart from setting up a Google Drive, we also need to set up a Google Colab account as well. And later on, we will prepare a Jupyter notebook and upload it to the Colab for execution and training. On the other hand, of course, we can also develop the notebook under the Colab. And it depends on whether you want to work in your local computer or you want to work under Colab. And I personally like working in my local computer, but I don't see there's a big difference between the two approaches. Once we set up the Google Drive and Colab accounts, we can then execute the code in Colab and following a few steps to mount our Google Drive. And I will show how we can do that later on. Now our Google Drive and Google Colab are ready. In step 3, we need to set up the data for training our custom object detections. Thanks to the contributions of original.NET in PJ Ready, Alice's AB has further improved their setup and network, such as providing Windows support, improving training speeds, and constructing YOLO v4 and etc. Although many folders and files are unnecessary, to keep everything simple, we just clone everything from the Alice's AB.NET. Once you clone the .NET into the Colab, on the left-hand side in Colab, you should be able to see a list of folders and files. And then we need to configure a file called makefile in such a way that the GPU and OpenCV are enabled. And there are 3 modifications inside the makefiles, and we will change the GPU equals to 1, CUDNN equals to 1, and OpenCV equals to 1. And because the makefile is under .NET directory, in order for us to modify it, we need to type in %cd.net to change the current directory to .NET. And we will then use SED functions for replacing the text in the makefile. SED is a stream editor, which means editing the files as a stream of characters. To replace a text using the Unix SED command, we have to pass the search strings as well as the replacement string. By default, the SED command does not edit the files and displays the outputs on the terminal only. So we have to add the -i options, which stands for in-place editing. The -i options comes in handy to edit the original file itself. If we use the -i options, the SED command replaces the text in the original file rather than displaying it on the terminal. On the other hand, / is used to substitute the file expressions. Say, for example, for the OpenCV equals to 0, we are going to substitute it with the OpenCV equals to 1 in makefile by using this /. Once we use the SED command to edit the makefile to use GPU, CUDNN, and OpenCV library. Following that, we can put down the make command to compile the .NET from the new makefile. For a quick summary, in step 3, we will clone the .NET from Alice's AB and then configure the makefile inside the cloned .NET for enabling the GPU and OpenCV. And finally, we will compile the makefile and darknet. Once we compile the darknet, we need to copy a configurations file and make some changes for setting up the training parameters and customize the number of outputs. So in step 4, there are two common pre-trained YOLO3 network that we can work with, which are YOLO3 Tiny and YOLO3. So if we wanted to build our own custom object detections based on either YOLO3 Tiny or YOLO3, we can modify their configurations file accordingly. I would like to emphasize that YOLO3 Tiny is faster in output, but lower in accuracy. So in the programming exercise that I'm going to show you later, I will use YOLO3.cfg instead of the YOLO3 Tiny, because I wanted to have a higher accuracy in output. Therefore, I didn't try to build a custom object detections based on the Tiny version. But I believe that the steps for building based on YOLO3 Tiny and YOLO3 are very similar. So I will show you here for reference, although I didn't try it before. And here I separate this step in 4A and 4B to illustrate what we need to modify for YOLO3 Tiny and YOLO3 respectively. So let's go through the YOLO3 Tiny configurations file first. And in the very first step, we just need to make a copy of YOLO3 tiny.cfg files to make sure we always have the original copies for further modifications or for other exercise. And of course, it is not a must to make a copy, but it is just a good habit to do so. In here, we will use the cp, that is the copy command, to copy the configuration file. And here you can see that the first parameters is the file and that you want to copy. And the second parameters is the file names that you wanted to use for that copy. Once we duplicate the YOLO3 tiny files, we will make several changes in the file. We need to change the line batch to 64. This means that we will be using 64 image for every training steps. And then we need to change the line subdivisions to 16. That means the batch will be divided by 16 to decrease the GPU VRAM requirements. And then we need to change the line mass batches to at least classes times 2000. In other words, we wanted to set the number of chain link according to the number of classes, and that is directly proportional to our numbers of classes. For example, if we only have one class, we might want to set the mass batches to at least 2000. And if we have two classes, we set it to at least 4000, and so and so. And then we need to amend the total number of filters according to the total number of custom objects in line 127 and line 171. And the number of filters is well defined by an equations, which is that we add the number of classes by 5 and then multiply the sum by 3. For example, if number of classes equals to 1, we need to set the filters to be 18. And if the number of classes equals 2, we will set the filters to be 21, and so on. Finally, we also need to amend the number of classes in line 135 and line 177, which represents the number of categories that we want to detect, or you can say that that represent the number of objects that we want to detect. For example, if the number of objects is 1, we set the classes equals to 1. And if the number of objects is 2, we set it equals to 2, and so on. Here, I just create 3 slides for ease of your reference. Please feel free to print screen for your own usage. And this slide shows the configurations for one classes. And this slide shows the configurations for 2 classes. And finally, this slide shows the configurations for 3 classes. Now, let's see how we configure YOLO3.cfg files. These steps are very similar to configuring YOLO3 Tiny. So we will just use the cp command, and that is the copy command to copy the configuration file. And the first parameter is the file that you want to copy, and the second parameter is the file's names that you want to use for that copy. And similarly, once we duplicate the YOLO3 v3 configuration file, we will make several changes in the files. We need to change the line to batch to equals to 64. This means that we are going to use 64 image for every single steps. And we need to change the line subdivisions to equals to 16. And that means the batch will be divided by 16 to decrease the GPU VRAM requirements. And then we need to change the line mass batches to at least equals to the classes time 2000s. In other words, we want to set the number of chain link according to the number of classes, which is directly proportional to the number of classes. For example, if we only have 1 classes, we just set the mass batches to at least 2000 and so and so. And then we need to amend the number of filters according to the number of custom objects in line 603, line 689, and line 776. And the number of filters is defined by the equations, which is that we add the number of classes by 5 and then multiply the sum by 3. For example, if number of classes equals to 1, we will set filters to be 18, and so on. And finally, we also need to amend the number of classes in line 610, line 696, and line 783, which represent the number of objects that we want to detect. For example, if the number of objects is 1, we set the classes equals to 1, and if the number of objects is equals to 2, we set it equals to 2, and so on. Again, I summarized the steps for 1, 2, and 3 classes in 3 slides for ease of your reference. Please feel free to print screen for your own usage. And this slide shows the configurations of YOLO3.cfg files for 1 classes. And this slide shows you the configurations of YOLO3.cfg files for 2 classes. And finally, this slide shows you the configurations of YOLO3.cfg files for 3 classes. In our programming exercise shown later in this video, we will apply YOLO3.cfg files for detecting 2 classes. So we are going to configuring these YOLO3.cfg files. So we will use SED functions with -i in place editing options for replacing the corresponding texts. In the first line, we update the batches equals to 64. In the second line, we update the subdivisions equal to 16. In the third line, we update the mass batches to 4000 because we have 2 classes. And then we update the filters equals to 21 in lines 603, 689, and 776. And we also update the classes equals to 2 in lines 610, 696, and 783. To make sure everything is correct, once we run the codes in Colab and update the YOLO3 training files or YOLO3 tiny training files, we can download the corresponding files and open it, and then press Ctrl F and type in square bracket YOLO. And there should be 2 matches for YOLO3 Tiny and 3 matches for YOLO3. Once you press Find Next buttons, you should be able to see 2 changes. Under the YOLO layers, the classes must equals to the number of objects that you wanted to detect. For example, if you are having single class object detections, the classes must equals to 1. And if you are having 2 classes object detections, the number must equals to 2. And under the convolutional layers before the YOLO layers, the filters must be equals to the numbers calculated by the equations that I showed before. For example, if you are having single class object detections, the filters must equals to 18. For 2 classes, the filter must equals to 21. And then you press Find Next buttons again to search for the next YOLO layers. Remember, there will be 2 matches for YOLO3 Tiny and 3 matches for YOLO3. In the next steps, step 5, we need to create a doc names files for our classes. Inside the document, there is a data folders. In the folders, you can see there is a coco.names files, which is used to store the 80 class names. Because we want to have a custom object detections, so we also need to create a doc names files for us to store the class names. So in order for us to create a doc names files, we are going to use the echo functions, which is used to display a line of text. However, it will just print out the text as it is. So we also need to add -e options for us to make the echo interpret /escapes characters. And the /n indicates we need to add a line. And then we will use the greater than sign to save the files into the data folders with the file names as obj.names. Once you create the .name files, you can download the files and check whether the classes are displayed correctly inside the files. And that's it. Each line should contain 1 class only. And if you have 1 classes, then you should only have 1 line. And if you have 2 classes, then you should have 2 lines, and so and so. And the next step is also to create a files. Inside the same directory, there's the data folders. We will also need to create a obj.data files to specify the following 5 things, which basically indicates how many classes that we are going to train. And it also specifies the locations of train.test, test.test, and obj names files. And also it specifies the locations where you want to store your YOLO weight files. So we are going to use echo functions with -e options again for creating the doc data files. Just for better illustrations, I separated the codes by 5 lines, but indeed, in the program, you should only see 1 line of code. So say for example, we will have 2 classes. So we type the classes equals to 2, and we specify the locations of the train.test, test.test, obj.name files are all inside the data folders. And finally, we are going to save the trained YOLO weight files in the folder called YOLO3 in our Google Drive. And once you created the doc data files, you can download the files and check whether the contents are similar to what we have in the screen. In step 7, under the same data directory, We will need to create a folder in such a way that our image can upload and store there. Here we simply use the mkdir functions to create a folders called obj as shown in the screen. And then we will unzip our image database and upload to the obj folders. We simply use the unzip functions to locate our zip files in Google Drive and then provide the directory where we want our images to be stored. And that's the obj folders we just created. And after unzipping the file, you should be able to see two types of files, which are JPG and text files. The JPG files are the images that you want to train, and while the text files contain the object class and annotations informations of the image. Just wanted to provide you more information. So for example, in step 1, after using the label image tools to create our image dataset, we should have a file containing the class informations and annotations informations. The 0 and 1 in the notepad represents the class informations because in our example, we are having two classes. We will have two numbers. In our example, 0 is wearing mask and 1 is not wearing mask. And then the four numbers following the 0 and 1 are the annotations informations for the square, which provide us the x and y coordinates of the center of the square and the width and height of the square. In short, in step 7, we are going to create a folder inside data folders, and then we unzip and upload our images and the associated text file in the folder. The next step, step 8, is to create a train text file. Once we create the OBJ file folders for storing our image, we also need to create a text files that contains all image with their file names and path. As shown in the pictures, we need to provide the path and file names for each of the image, and each image should be in new line. And in this step, we can use Python code. So we import glob modules, and then we use glob.globs to get the file names with file path for all JPG files. And then we use the open functions in write mode to create the train text files and write the file names and file path line by line into the files. And after running the code, we should have a similar test list as shown in the right-hand side of the screen. The second last step is to download the pre-trained weight for the convolutional layers under the dataset directory. Remember what we discussed before about the transfer learning. So for training our custom objects, we use the convolutional weight that are pre-trained weight and then start our own training from that particular trained weight in such a way that we do not have to retrain everything from scratch again. For YOLO3, we are going to download the pre-trained weight from the .NET 53 models in pjready.com website. For YOLO3 tiling, you might want to follow the instructions in Alexis AB GitHub. You probably need to download the weights and then use an additional command to get the required pre-trained weight. However, this is a bit out of the scope of these videos, so please feel free to try it and share with me if it works properly. Finally, we get there. For YOLO3, we just simply run the command to start training, and there are three parameters that you need to input for custom object detection training, and that includes the first one is the data/obj.data, which is used to identify our training informations such as number of classes and locations for saving rates, and so and so. And then the second parameters is the CFG slash YOLO3 training.cfg files. That is for identifying our training network configurations. And then the last parameter is the .NET 53.conv.74 for identifying the pre-trained network. So once we provide all these parameters, we are ready to start training our custom object detection. A friendly reminder here is that from time to time or sometimes you might lose your connections to Colab or stop this somehow in the middle of training. So in order for you to continue to train on your latest weight, you can replace the final parameters with your last saved weight in Google Drive. In that case, you don't have to restart your training again, and that could save a lot of times as well as your previous efforts. On the other hand, for YOLO3 Tiny, again, please visit Alice's AB GitHub for further information. I believe the command is more or less the same, except for the pre-trained network. So, this is a very quick summary for what we've covered in the key steps. I use the command line as a reference point because everything we do is to execute this command line properly. As mentioned before, there are three parameters inside this execution command, and we can separate this command into four key inputs, and that is the darknet detector train, data slash obj.data, cfg slash YOLO3 training.cfg, and also the darknet 53 conf.74. So in step 3, we clone, configure, and compile .NET in Colab so as to set up the training environment properly. And then in step 4, we configure the configurations files based on the number of objects in order for us to perform custom object detection. In step 5 and 6, we create a name file for class names, and then we also create a data files for identifying the number of classes as well as some important path. And then in step 7, we create an image folder in Colab so that we can upload our images from Google Drive to the folders in Colab. Remember that before we upload the image, we also need to prepare the image dataset. So in step 1 and 2, we need to use label image tools to label the custom objects in YOLO format. Once we set up the image folder, we can then create the train.txt files based on the file names and path in the image folder. Finally, in step 9, we download the corresponding pre-trained weight for training. And then in step 10, we execute the command for starting our custom object detection training. And that's it for training the custom objects. And the next thing we need to do is to download the result and perform the custom object detection. In order for us to perform custom object detections, we can simply download the trained weight, configuration files, name files, and use the deep learning framework in OpenCV, which is compatible with YOLO. And the advantage of this is that it works without the need to install anything, except that we need to install the OpenCV. And just one friendly reminder is that the versions has to be at least 3.4.2. So first of all, we go to our Google Drive and download the last weight files, or you can download the previous weight, say for example, 1,000, 2,000, or 3,000, if you suspect there is an overfitting occurred. Here, what I mean is that overfitting is the case that when you can detect objects on an image from training dataset, but can't detect objects on any other image. If that is the case, you better to try out with the previous weight rather than the last weight. And then we can download the YOLO3 testing configurations file as well as the classes test files. And finally, we can simply open a terminal to pip install OpenCV Python. And that's it. At the end, we will put everything under the same folder with the object detections Python file to perform single or multiple object detection. To start custom object detections, we first need to prepare our image dataset in our local computers. And there are many ways that you can prepare your own image from different sources, or even you can take photos by yourself. But what I did is that I tried to search the image in the internet with the use of combs. So in order to facilitate to download all the image once, so I just add these extensions, download all image to my comb. I just show you as an example. I add the extension right here, and then once I has this extension, I search wearing mask people. And then there's a little icon right here, zip. I just click the icon, and then I can download all image in a zip file right here. Once I have my own custom image, I can then download the label in, which is a graphical image annotations tool for me to annotate my image and prepare a recognized text format for the YOLO training. As mentioned before, I will download the latest versions for Windows. So once I download, I can just prepare these two zip files into a single folder. And then I will create a image folders, and I will extract all the image to this image folder. And then I will run the label in executions file. Once we open the label in tools, we need to set up two directories. The first is the open directory, and the second is the change save directory. So you just have to locate your image dataset. So here you can see that the image is inside this image dataset. So we select the folder and then change save directory. So we just click on the desktop, image dataset, image, and also select the same folder. And the next thing that we need to do is to change the format from Pascal to YOLO. And the next thing is to create the rectangle box for your custom object detections. Say, for example, here, this is wearing mask. Similarly, for this gentleman here, is wearing mask. So once we just create two rectangle box, we can then save the labels to files, and then we can click next. We can continue this exercise until all image here are annotated. Because I have two class here, one is wearing mask and the other is the not wearing mask, I want to show you how to do that. So, yep, here I create another class here that is the locked wearing mask. And then this is the wearing mask, and so on. After using the label IMS tools to create our image dataset, we should have a file containing the class informations and annotation informations corresponding to each of your own image. And the 0 and 1 in the notepad represent the class informations because in our example, we are having two classes, we should have two numbers. Here you can see that the first class is 0, and then the second class should be 1, and that means that 0 represents the people are wearing masks, and 1 represents that the people are not wearing masks. And then there should be 4 additional number for each of the entry. So for the first two number here, which are actually the x and y coordinates of the center of the square, and then the last two numbers here are actually the width and height of the square. And because we have 8 objects, so there are 8 entries inside this notepad. And now we have all the images ready, so we can just put everything in a zip files and then upload to our own Google Drive. As mentioned before, we also need to set up a Google Drive account for uploading and downloading files between Colab and our local drive. So in our example, we are going to create a folder called YOLO3 under my drive. So, and then we are going to upload our image .zip file into these YOLO3 folders. Just a friendly reminders that the names of the folder and also the names of the zip file should be the same as shown here. After uploading the datasets as image.zip into the folder YOLO3 in our Google Drive, we can then log into the Colab. And then in the file buttons here, we can upload our notebook, and we can choose the file which I prepared for you, which is called the train YOLO3 multiple, which is a Jupyter notebook. And let's go through this Jupyter notebook line by line. So let's see if we have the GPU first. Here you can see that we have the notebook setting. We can pick the non-GPU or TPU. Here we are going to pick the GPU. And then we are going to run this line to check whether we have any GPU that can allocate to us. Okay, we have a GPU right here. You can see that. And then we just want this code to mount our Google Drive. We click on this link and then click on my account and copy this sign-in code, and then just put the code here and then press enter. And that's it. Our Google Drive now is mounted. Here, this code is used to create a symbolic link to link up the Google Drive, so we do not have to type in the full links again. And then you can also check that your G drive, that is the Google Drive, is already mounted under this Colab file. So we just follow through the step that I mentioned before. First of all, we clone the .NET, and then we configure it. We configure it by setting the OpenCV to equal 1 and GPU equal 1, and also the CUDNN equals to 1 under the make file. And then we are going to compile the document. So the next step is to configure our YOLO3.cfg file. So here you can see that there is a CFG folders right here, and then that should contain the YOLO3.cfg file. That is this one. We are going to make a copy under the same folder, which is called the YOLO Wi-Fi training. So let's run this code. And then we are going to change the lines in these YOLO Wi-Fi training configurations files. Just like what I mentioned, it depends on how many classes of objects that you would like to detect. So for the batch, we are going to change to 64. For the subdivisions, we're going to change it to 16. And then the mass batches depends on the number of classes that you are going to detect. Say, for example, we are going to detect for 2 classes, so we should set it to 4,000 based on the equations. And then we are going to change the classes to 2 in this 610 line, line 610, line 696, line 783. And then we are also going to change the filter from 255 to 21 under the YOLO layers. And then at line 603, line 689, and line 776. Actually, you can download the YOLO Wi-Fi training CFG files here to see whether you already make the change successfully. But I'm not going to show here. On the other hand, there's another way that you can create these configurations. Say, for example, you can actually create under your local computers and then upload to your G drive. But it doesn't matter. These two approach can get similar results. So, and then we are going to create a .name files and also the .data files. And under the .names files, we are going to have 2 classes. So that means we have to type in the class names. So that includes the wearing mask, not wearing mask. And then we are going to set up the obj.data files here. So these doc data files just provide you, just tell the .NET that we are going to have 2 class, and then we are going to, the train test file will be located in this path, and then the validate file is going to be in this path, and then the name file will be in this path. And then we are going to save our weights in our Google Drive under the YOLO V3 folders. So we are going to create the name file, .name files, and also the .data files under the data folders. Let's see if we created that successfully. Here you can see that there's a data file. Yep, we have the obj.data and obj.names file here. And then we are going to copy these two files from the Colab back to your Google Drive so that later on we can just download these two files from the Google Drive. The next step is that we are going to create a folder, and then we are going to unzip all image under this folder. And this should be under the folder data .obj. This should be this folder. So all the image and the text files are unzipped successfully under these obj folders. So finally, we can just create a train text files to locate the image files. So we just run this code, and then let's see where is the train text file. That should be under the data. That should be under the data file. Yep, right here, and then we can double click it. And you should have a similar text files shown here. And finally, we can just download the .NET 53 conf.74, but it takes some time. I will just click it and then pause here. Welcome back. So we are almost there. So once we download these pre-trained weights for the convolutional layers files, we can then just run the last tranche of codes to start the training. Yep. So here I would like to mention that these codes is that you can use that to start your training from at the very beginnings. So just say, for example, if there's any problems in the middle of your training and that you would like to retrieve your last weight, you can just comment these files and then uncomment this code, and then you can train your YOLO starting from your last waiting. But because we have nothing at this point, so we are going to train it from the start. You can see that the GPU count 1. That means we are using GPU, and the configurations file is set up like needs. So now it's training. So always remember that the weight file will be automatically saved in your Google Drive. So what you have to do is just to download the weight from the Google Drive later on. After 4,000 training or 4,000 iterations of your trainings, you should be able to see there a list of files under your YOLO3 folders in the Google Drive. So what you need to do is to download the class text file, download the YOLO3 testing configurations file, and also download the last weight files. And then we will put everything under the same folder with the object detections Python file. Before we move on to the object detections Python files to perform the multiple object detections, I would like to show you how we could adjust the code in order for us to perform a single or any other multiple object detections. So here, what we need to change is to change this mass batch number. Say, for example, if we would like to perform a single object detections, so we just need to put it back to 2000. The class changed to 1. The class changed to 1. The class changed to 1. And then filter changed to 18 according to the equations. 18 according to the equations, and 18 as well. And then the second things that you need to change is that you just only need to provide one classes and save in the object stock names files. And then here you need to change it to 1. And of course, you also have to prepare your image files to only a single class. So on the other hand, if you would like to change it to the to free object detection, so here you can just change it to 6000 free, 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 and then this one should be 24, 24, and 24, and this one should be free. And here you just add few more objects that you would like to detect. Say, for example, second item, and then per item. Finally, we can open the object detections Python files, and the details of this code is that I already explained in other videos, which is called the Python real-time object detections with YOLO3 and OpenCVs. So I'm not going to cover it again in these videos. So what you need to do is just to make 2 changes in these videos in order for you to perform the multiple object detections. I should say that should be the custom multiple object detections. So you just need to change these names and also this name under the original code that I provide in the other videos. So here you just put the weight as the YOLO3 trailing last weight. And then on the other hand, for the configurations, you just need to change it to the YOLO3 testing. So, and then I prepared it, 2 videos here in order for in order for me to show you how we perform the 2 classes multiple object detections. Nothing else you have to change. You just change these 2. You just have to change these 2 names. So just one. And here you can see that there are 2 person wearing masks and doing exercise. So I'm not going to take too long on this. I'm going to stop it. And then the second case is that there's a lady that who is not wearing mask. So you can see that this is the second class. So again, I'm not going to take too long here. And that's it for this video. I hope you enjoy and thank you for watching. If you have any questions or suggestions about what we covered in this video, please feel free to ask in the comment section below, and I will do my best to answer. And if you enjoyed this tutorial, you can subscribe my channel, simply like the video, and it is a great support to share this video with anyone who you think would find them useful. And thank you all for watching.